We've all seen FEA models that aren't stable, but what do you do when your fixtures are correct, inertial relief and soft springs both have no effect? This little trick might just help you out. So before we get into the FEA of the part, I just want to show you this, my current favourite mate of the moment, which is the width mate. So you select 4 faces, and if you select those and hit the width under advanced mate, it'll actually do the 2 parts symmetric about each other. Saves a ton of time and faffing around with distance mates. So with it all mated up correctly, and I can now enter the simulation environment, and we're going to create a new static study, and we're going to apply a fixture to the bottom of the main pin. Now through the main pin is a little cotter pin, and there's a piece of sheet steel which I'm going to apply a roller fixture to, and that's going to allow it to bend up like a banana but prevent it from spinning round, which is going to help with some large displacement problems. So from then we're going to set up the contact sets, and this is basically the crux of this tip. There's some weird settings in contact that I've never come across. So if you're not familiar with contact sets, basically it's the way you tell the FEA which bits touch each other within an assembly. So generally within the blue section you select the smallest face, so in this case with the smallest area, so the inside of this pin, which takes me a couple of goes to get, the inside of the sheet, and then the larger part goes in the pink box. And basically that was explained to me by our CAD reseller. That's all about the efficiency of the how the nodes to the elements connect. So it's basically more computationally efficient if you actually have the smallest face area in the blue section, the larger one in the pink section. So the final stage is to define the contact set between the cotter pin and the main body. And now what I'm doing here is using the select other as the face is currently hidden. Now you've got to be careful when defining contact sets. If you miss one, the study will actually run, but it can give unreliable results. What happens if you miss a contact set is it will default to the global setting, which tends to be bonded, and it'll treat them as though they've been welded or glued together, which isn't always what you want. So now I'm setting up a force, and basically there's going to be a force on the underside of the sheet that's going to have 3 effects. It's going to bend that piece of sheet, it's going to introduce some kind of shear force into the cotter pin, and a tensional force throughout the main pin. So the next step, once you've defined all your contact sets and forces and fixtures, is to set up the mesh, and there's various settings under the mesh parameters. I chose curvature-based mesh as I have cylindrical elements. I did try the blended curvature-based mesh, but that gave me an imbalance, and it gave me some weird translations when I actually ran the simulation. So ignore the fact that the mesh is absolutely massive. For the real part, I actually refined the mesh size in the relevant areas and got it working just as I want it. Now this next little trick is something that I learned on a support call with my CAD reseller. Sometimes you'll be running the simulation and you'll just get these static green bars and you'll think, what's happening here? Has the thing frozen? So if you hit on the convergence plot, you can actually have some amount of faith that the computer is crunching through the values, and no doubt this will show to someone much more intelligent to me some useful information. But as far as I can see, the only thing I use this for is to show that the simulation is actually chugging along and something's happening on very complex assemblies with lots of contact sets and friction and all kinds of things like that. It can take maybe an hour to crunch the numbers, so this just gives me a bit of faith that it is actually doing something. And then after all my efforts, I'm rewarded with this message that excessive displacements have occurred. So the chances are that this is that cotter pin flying out into infinity and beyond because there's no restraints on it. So the standard approach to this is to either define it better with the fixtures, or if you don't want to constrain its motion in any particular way, then there's a couple of options in the study properties in which you can turn off soft springs or inertial dampening, and what that does, or inertial relief I think it's called, and what that does is it sort of almost puts the thing in treacle, and it just gently pushes the thing back into position if there's an imbalance of forces. Because of course, according to Newton's laws, if you put a small force on an object effectively in zero friction, zero gravity environment, it'll just fly off into infinity and beyond, and that's what these two settings are here. And under normal circumstances, you might expect that to solve the problem. So I press run study again and turn on my convergence plot just to give myself some faith that the things are working. And I'm going to get another error in a second, which is new to me and ended up in me calling the CAD reseller. So this is the error message I got. It says equilibrium is not achieved, and this was something that my technical support was able to help me with, something that they can do in half an hour generally would take me an afternoon of trawling through forums. So I'm very grateful for the help, and I wanted to share this trick with people as it's not something that I've come across before. And basically what it comes down to is the way the contact sets. So if you go into the simulation options, default options, mesh, and then tick this, which is show advanced options for contact set definition. it will give you an extra option when you define your contact sets. And what that extra options allows you to do is choose surface to surface, node to surface, etc. What we want in this particular circumstance is surface to surface. And basically what that prevents the simulation from doing is pivoting one body around another on a vertex, much like if you were to spin a cube on a corner. It just helps lock the assembly down and get it to behave how you want it to. So I'm going to do that on all three of these contact sets that I've defined, and I'll run the study again. And under these circumstances, the study ran and it actually found the equilibrium. It gave me some quite sensible displacement plots, although you will notice they are slightly asymmetric, which suggests that there's an imbalance in the mesh somewhere. Now, I went on to find out that you can sort this imbalance out through the use of split lines, and you can force the mesh along the split lines, but it's a bit outside the scope of this video. Now, you will notice under the von Mises stress that you'll see in a second, you get some ridiculous values, and that is simply just a stress singularity, which again is a rudimentary FEA concept, and perhaps I'll do it in a different video. Do let me know if you want to see some more FEA topics like this. So the model is behaving as planned. We've got a force pushing up from below, we're inducing a stress in the pin, we're getting a bending force or moment in the bar, and displacement looks sensible. You'll notice that green roller slider there is allowing the bar to bend upwards, but it's stopping it from spinning. If I was to put a roller slider on the end, then that would artificially constrain the bar, and we wouldn't get necessarily realistic deformation. But here we can see that that mesh is ridiculous. If you look at the red spots, yes, they are singularities, and I've iso clipped here just to highlight that, but there's hardly any elements within the high stress area that I'm interested in. So from this video, the next step is to maybe put a couple of fillets on those and then refine the mesh further, check the stress hotspots tool, and just check that you're getting sensible results. Now, if you like these videos, do like, subscribe, and comment below to let me know what other topics you would like me to cover. And until then, I'll see you next time.